At first glance, looking at all these cables and trying to figure out where they belong can seem a bit overwhelming. But once you understand the simple pattern behind it, everything starts to make sense. Today I'm going to show you how to wire a simple single-phase fuse board, breaker panel, consumer unit, whatever you call it. In the last video I explained what live, neutral and earth are. We learned that every circuit in your house is just a combination of those same conductors repeated throughout the installation. So naturally, the next step is learning how all those wires come together inside a panel. I'll be using French equipment, but don't worry too much about the exact devices. The equipment may look different in different countries, but the principles are the same. Let's imagine you built a small kitchen extension. Instead of running every cable all the way back to the main panel, you've installed a small sub-panel inside the kitchen and brought in a supply cable from the main panel. You've already run all the wiring, installed the sockets and lights, and now it's time to connect everything. In our example, we have 5 circuits: induction hob, oven, dishwasher, kitchen sockets, and lighting. The cables are already labeled on the panel side, and we also have our supply cable coming from the upstream panel. This cable brings power into our panel. Our job today is simply to distribute that power to all of these circuits. One thing to note before we start. This example uses a single-phase panel, so you have one live wire, one hot wire. In the United States, homes use split-phase power, so you'll typically have 2 hot conductors, 2 live conductors instead of 1. In some countries, homes may be supplied with 3-phase power, meaning you'll have 3 live conductors. That changes some of the details, but not the principles we're covering today. Power still comes into the panel, gets distributed to individual circuits, and is protected by breakers and RCDs. So even if your panel looks different, the logic is exactly the same. Now I'll strip the installation of the other cables, and since I prepared a simple circuit schedule, I will just remark them by numbers. Before we start connecting anything, let's quickly remind ourselves what each wire does. The live conductor delivers power. The neutral conductor provides the return path. Together they form an electrical circuit. The earth conductor is different. Its job is safety. It connects all exposed metal parts together and provides a low resistance fault path if something goes wrong. Under normal operation, no current should flow through the earth conductor. Because the earth is not part of the circuit, no current is flowing through earth wires, so they never need to be protected by breakers. You always connect them directly, all together, via bus bar. I'll remove this rail with the breaker so we have more space. First I'll connect the incoming supply, leave it a bit longer. Then we connect all the earth wires from the outgoing circuits to the same bus bar. Okay, I've tried to leave a loop, but there's really no space in this fuse board, so I leave these wires shorter. Small loop. Now all metal parts that will be connected to those circuits are connected to earth. Now it's time to wire our lives and neutrals. These are part of the circuit, they are current carrying conductors, so we need to find a way to protect them from overcurrent. If too much current flows through those cables, they can overheat and cause fires. That's where circuit breakers come into play. Get rid of the RCD for now. You install the breakers between your incoming supply and each outgoing circuit. Each circuit has a breaker sized appropriately for the cable installed. For this example, I've already selected the correct breakers. 32 amps for the induction hob, 20 amps for oven, dishwasher and kitchen sockets, and 10 amps for lighting. The exact sizing rules vary from country to country, so today we'll focus on the wiring rather than the breaker selection. These are French breakers. Both live and neutral are passing through them. This is an input side, this is an output side. But for now, let's wire the panel the way it's done in most countries. In most installations, the neutral conductors are connected directly to a neutral bus bar. I'll remove the rail with breakers again. For now, we'll connect our incoming neutral supply to a neutral bus bar. And then all the outgoing neutrals to the same bus bar. I'll actually just do them in the right order. And now it's time to connect our live wires. Let's connect just one circuit for now, an induction hob. We connect our supply live to the input of the breaker and the live that goes to the hob to the output of the breaker. Now we have one complete circuit wired. Let's stop for a second and look at what we've just built. The incoming supply brings power into the panel. The live conductor passes through the breaker and goes out to the circuit. The neutral conductors are connected to the neutral bus bar, and the earth conductors are connected to the earth bus bar. That's the basic pattern you'll find throughout this panel. Once you understand one circuit, you'll understand all of them. Now we simply repeat the same pattern for the remaining circuits. At the moment, our incoming live conductor is feeding only one breaker. To power all the breakers, we need a way to distribute that live conductor across the entire row. There are several ways to do that. You can link the breakers with short pieces of wire. It goes from this one, and then from this one, and then from this one, and so on. But most breakers use a comb. It's a solid piece of copper wire with insulation on the top. It's faster, neater, and usually more reliable. Then you simply connect your live to the same terminal. On some equipment you can connect the comb and incoming supply under the same screw under the same terminal, and on some other equipment you will need to use a special connector. At this point the panel will actually work. The live is distributed through breakers, the neutrals are connected to neutral bus bar and earth to earth bus bar. Now in a three-phase panel, the breakers will be distributed across three live conductors or three phases, so you couldn't use a simple comb like this. You would have a phase 1 connected to the first breaker, phase 2 to the second breaker, phase 3 to the third breaker, and phase 1 again to the fourth breaker, and so on. For that purpose you have special three-phase combs, which is like three combs connected into one. The neutrals and the earths will be connected the same way. In a split-phase panel, so in the US, the breakers are typically arranged in two columns, each supplied by one of the two hot conductors. Again, the neutrals and earths are connected the same way, through their bus bars. Anyway, let's test all of this now. Turn the breakers off, turn the supply on. Here I've installed a separate disconnect switch, so I'm going to turn it on. And now we have power here at our input. Now I test for voltage between the incoming live and the neutral. So that's good, and you have it on each breaker thanks to the comb. Now between live and earth. And now between neutral and earth. They are on the same potential and shouldn't be any voltage between them, so this is good. Now we turn the breakers on one by one. Now we test at the induction hob connection itself. There are small holes on top of these vagos, so just put it here. Live and neutral. Live and earth. Good. Let's turn all of them. Test the oven. Live and earth. Good. Kitchen sockets. So see, these two are on the same circuit, the cable just goes from one to another. And the next one. And the lighting circuit we're simply testing by turning the switch on or off. Good. And now you can safely disconnect any of your circuits by turning the breaker off, if you want to work on the light, for example. Now we've tested everything and confirmed that electrically our panel is working. I'll turn the disconnect switch off. But modern installations require another layer of protection, an RCD. In the United States, the equivalent protection is called GFCI protection. An RCD doesn't protect against overloads or short circuit. That's the breaker's job. Instead, it protects people from electric shock. So how it works? An RCD works by comparing the current going in through a live wire with the current going out through a neutral. It should be the same. If 10 amps leave through the live conductor, the RCD expects exactly 10 amps to come back through the neutral conductor. If some of that current finds another path back to its source, through a damaged appliance, wet surface, or through a person, the numbers no longer match. The RCD detects the difference and disconnects the power almost instantly. That's why RCD protection is required in most modern installations. Because an RCD compares the current flowing through the live and neutral conductors, it needs both of them connected to it. Up until now, our incoming live was feeding the breakers directly, and our incoming neutral was connected directly to the neutral bus bar. We're going to move both of these connections through the RCD. This side is where the power comes in, live, neutral. And this side where it goes back out to the circuits. So we connect live and neutral conductors to the input terminals. Then take the live output and feed the breakers. On this equipment we can do it easily with a comb. We just need a bigger comb. Now the RCD's output feeds the breaker's input. Now take the neutral output and connect it to the neutral bus bar. It's much easier to use a stranded wire and then ferrules, but I just don't have it here and I can't be bothered to go and get it from the garage in this heat. Now let's stop again and see what we've done. Threads are connected the same way, we didn't touch them. Our supply live and neutral connect to the RCD's input. They pass through the RCD, which measures the current in both conductors and compares them. Then on the RCD's output side, the neutral connects directly to other neutrals via bus bar, and the live gets distributed to each breaker, which protects all the outgoing conductors. Let's test everything again. Turn the supply on. Now we have power here at the RCD's input, but not at the output. We turn the RCD on. Now we have power at the output and at the input of each breaker. Not here, this is nothing. We can test it here. This is our output neutral. Or on a bus bar between live and neutral. Turn them all on. Let's test our kitchen sockets. Now to test the RCD under real conditions, I can use a socket tester. When I press the test button, the tester deliberately creates a small leakage current to earth. The RCD sees that some current is no longer returning through neutral and immediately trips. So we're there. Most RCDs also have a built-in test button. You should operate it every few months to verify that the mechanism is still functioning correctly. Up to this point, we wired the panel the way it's done in most countries. Now let me show you how we typically do it in France. So as I mentioned before, these breakers have both live and neutral terminals. That means both conductors, live and neutral, are passing through the device. So we'll move each outgoing circuit neutral to its matching breaker. Before, I've connected them in the same order, from top down, like our breakers. Now we need to distribute neutral from the RCD's output to all the breaker neutral inputs. Neutral going to the bus bar is obsolete now. And now we just replace it with another comb. This is the same universal comb. Test everything quickly one last time. And our panel is complete. As you can see, wiring a fuse board isn't about memorizing dozens of connections. Once you understand the role of live, neutral, earth, breakers, RCDs, bus bars, you stop seeing panel full of wires and start seeing a simple pattern repeated over and over again. And that's exactly why understanding the principles is far more important than memorizing a particular panel layout. Well, I hope you found this video useful. If you did, feel free to like and subscribe, and see you in the next one.